Okay, so let's come through. So there are really 4 styles of MPI plus OpenMP programming, and it depends on what the interaction between your OpenMP parallel regions are and your MPI library calls. Now, to support these styles, MPI now has a threading interface. So there will potentially be overheads in having an MPI library which can cope with OpenMP. And you'd be quite annoyed if you had a pure MPI program and we took the system out for maintenance, and a week later we said the system's back, and you say my MPI code now goes 10% slower. Oh, that's because the MPI library can now cope with OpenMP. And you go, well, I don't use OpenMP. So MPI allows you to say, look, do I want to use OpenMP? Am I going to use threads? And if so, how am I going to use them? And that's to allow it to use the most efficient version of the MPI library, because making the MPI library able to cope with threading may introduce overheads. So the 4 styles are master only. All the MPI communications take place in the sequential part of the OpenMP program. So that no MPI parallel. So that is by far the most common and the easiest to do. What you do is you simply use OpenMP to speed up the calculation parts. You just say my MPI will take place in pure serial regions. No, and I just use OpenMP to speed up the calculation part. And then there, actually, the MPI library has to provide no real support for that. Funneled, all MPI communications take place with the same master thread, but can be inside parallel regions. So you are therefore saying, okay, I am going to do communication within a parallel region. I'm going to do communications in regions where there are multiple threads running, but those communications will always take place through the set. So there you would always put OMP master around your communications. Again, that means that the MPI library doesn't have to do much extra. Serialized is like funneled, except, well, what you're saying is I'm now going to make MPI calls within a parallel region, and any OpenMP thread can make the parallel calls. Sorry, any OpenMP thread can make the MPI calls, but I will make sure that no 2 threads are calling the MPI library at the same time. So it's up to you then to put your MPI calls, for example, in critical regions to make sure that you don't have any race conditions. So again, that's very little work for the MPI library to do, because you've said to it, look, you do not have to worry about any race conditions. I will make sure that only 1 thread is ever calling the MPI library at the same time. That's called serialized. Here you may have an issue that, actually, remember, MPI messages only go between different processes, but you might be saying, well, I am thread 3 on process 0. I want to send a message to thread 3 on process 1. How does you make sure that the receive on process 1 is for the message for thread 3, not another message? Well, you have to do that by hand, and the obvious way to do it is through tags. The standard thing to do here is to tag your messages with the thread ID. So that allows you to select. So remember, MPI just sends messages between processes. Here you want to send messages between threads. It's up to you to manage how the messages go to different threads. And you could have a separate communicator for each thread, but it's actually probably the simplest thing to do is to tag them. Is to tag the messages with the thread of the sender, for example. Now, there will potentially be race conditions on send and receive buffers and such like, but you manage them all. Okay. Multiple is the most general style. Okay. MPI communications, so any thread can call MPI at any point, and that means the MPI library has to be thread safe. Some MPI implementations don't support, they do tend to nowadays, but they tend not to do it very well. The reason is that the MPI libraries were designed 20 years, 30 years ago when there was no such thing as threading. And so mostly what an MPI library will do is will put lots of locks or critical regions inside. And so basically the MPI library is serial, but it's thread safe, but only by making sure that everything is protected and done serially. So although multiple is what you might want to do, it is, oh, sorry, apologies. Although multiples might what you want to do, it tends to be not particularly well supported and can have big performance implications. So for example, if you have a pure MPI program, and then you say, I want to do MPI thread multiple. I want to have an MPI library which can cope with being called by multiple threads at the same time. Your pure MPI program may go slower because there are a lot of more overheads in the MPI library. OpenMP master is very, very simple. Okay, you have work regions and communication regions, and you only put parallel. You only speed up the work regions, not the set. So that's very simple. Basically, to MPI, all you're doing is increasing the calculation speed with threads and doing the communication serially from the master thread or from the parent process, and that means that that's very simple to do and quite easy to manage, and may not give you good performance, but it is very simple to do. So master only is really quite straightforward. Funneled is a bit like master, except you do MPI calls within parallel regions, but you make sure that that they're only done on the master process. Now remember, here you have to worry about the fact that you may be doing some work here, okay, which updates some data. You're now going to send that data. Now you're going to send it from the master thread 0. However, you need to make sure the calculation is completed. So you need to have a barrier to set. Sorry, I lost my cursor here. You need to have a barrier to say, I need to make sure that all the work is finished so the data is ready to send. You need to have a crash flag with OMP master to make sure that only the master thread 0 sends it. I need a barrier at the end because OMP master doesn't have a barrier at the end, and you don't want to carry on doing any more work until that data has been sent. So although conceptually it's quite straightforward, in practice it's a bit more difficult to do, but that's how you would do it. OMP serialized is saying that I will do MPI sends within a parallel region, but I will make sure that no two threads are calling the MPI library at the same time, and that requires you to have a critical region, okay, OMP critical, which says that although all the threads are going to call this, they only do it one at a time. So, and here, I'm assuming here that this send, the data being sent here, doesn't depend on the work, okay? So each thread is only sending its own data. But again, the MPI library doesn't have to do much internally because you've said that you will only be calling it on one thread at any one time. OMP multiple is basically all bets are off. You just call MPI send anywhere. And that is a lot of work on the MPI library. It has to basically protect access to all its data structures because message queues, everything may be being updated by multiple threads at once, and to avoid race conditions, because the library was probably not designed with thread safety in mind, there will be lots of locks or critical regions or barriers or whatever within the MPI library. So making MPI libraries thread safe is difficult. You have to you either could have multiple data structures, one per thread. It probably doesn't do that. It probably just locks access to data structures. This has significant overheads, and therefore, to make sure you only incur the overheads which you require, you can select which version of thread support you need, and do that at the start. You don't call MPI init, you call MPI init thread, which I think is a bit of a weird name, and you say you give it the normal arguments of argc and argv, but you say what thread level you require, and it'll give you back what's provided. Okay, and required can be MPI thread single, MPI thread funneled, MPI thread serialized, or MPI thread multiple. Okay, so though you can request, but it will give you back what support it can give, and that may not be what's provided. Okay, sorry, that may not be what's required. So you might say, I want MPI thread multiple, but it might give you back MPI thread serialized. That's the highest I can do. And these numbers, you don't know what they are, but they're ordered. So what you should do here is you should call this, okay, and you should say on return, if provided is less than required, then print there's a problem here. Okay, so that is the interface is designed to basically say you say what level support you require. MPI will try and give you that, but it okay. Is there a special way of building it? I don't know. That's a very good question. That's a very good question. I think it's. I don't know how the MPI library copes with this. So that implies that there's multiple. Yeah, that's a good question. I don't know. I don't know. As I said, I don't have a lot of experience building MPI libraries. Well, I would definitely. What the thing to do is write a 5-line program that says, you know, call MPI init thread and ask for MPI thread multiple and see what you get back, and then print it out. I don't know. That's a good. I would expect that the default installation mechanism would build the most general purpose MPI library that it could do, but I don't know. That's a very good question. But yes, you just have to run a little. And most MPI libraries now, in principle, do offer all the levels of support because there are only really OpenMPI and MPI-CH basically, so they probably will work. How efficiently they do it is another question. It's a good question. I don't know. That's a good question. So these are monotonic. So MPI thread single is less than this, is less than that, is less than that. There's a slight distinction here because the slight confusion, because the MPI library is designed for threads, whereas we're talking about OpenMP, and so there's no distinction in these there's no distinction in these terminology between what we've called master only and funneled. So that's because the MPI library is designed for a general threading model when we're talking about OpenMP. So you maybe need to look up the details of how that works, but hopefully the concepts are reasonably clear. And again, my cursor seems to have disappeared. So you can also ask to do MPI thread query. You can ask what the current level of support is. So yeah, you might have a library routine which requires high level of support, and you can check that it be initialized correctly. So just finally, to go through the levels, master only is very simple to write and maintain because you've got this clear separation between the outer MPI and the inner loops, and you don't have to worry about synchronizing threads because basically all your MPI takes place in a serial region outside of parallel regions. The disadvantages are, we've talked about, all threads other than the master thread are idle during the MPI calls. A subtlety here, all the data is communicated by the master thread, which means it may screw up your caches. Okay? So all the data passes through the cache of the master thread. There's a distinction between inter-process and inter-thread communication. I'll mention that later on. And so, yeah, I mean, it's very, very simple. It's the model I've used, but it does have its disadvantages. You really need to have you need to have small communication overhead for this to work. That may be. So here's an example. Basically, we have it's a Fortran example. We have a calculation. We send data between processes with a send and a receive node. That calculation. Some of these messages on a shared memory system. Some of these messages will go within a node, and some will go between nodes. But they're all happening at the same time. The intranode and the intra and internode messages are all overlapped, which is good. If you were to write the equivalent master only code, okay, you would have this, okay, and now because you have this is only the internode communications. The communications between the nodes is done in some sense via via shared memory. The threads are communicating by reading back to thread, and so that's separated out. So there is an additional overhead there. The inter-thread communication happens separately from the intranode, and that may harm your performance. And there's also, of course, an implicit barrier here, because at the end of any parallel do, there's a barrier. So there's extra synchronization put in there. So you have extra synchronization, and the internode and intranode communications are now sequentialized and not happening at the same time. But if this is a huge amount of work and this isn't much, then it's probably okay. Funneled, it's still relatively simple to write and maintain. The nice thing here is with funneled that other threads can be computing while the master thread is in an MPI call. It's harder to write because there's less clear distinction. And we still have the issue that the data pass through the cache of the master is and we don't overlap inter node and intranode communications. But a simple. Now, one thing you might want to do is with funnels is actually, you might say, well, actually, what we want to do is we want so we have a barrier, and then we're not going to master. We've got an OMP get thread num equals 0. If I'm the 0th thread, I do the communication. Else, you might want to do some computation. Okay, that's quite an attractive thing to do. You might say, well, I'll have one thread do the communication, but the other threads can do computation while that's going on. The problem is you can't use work sharing here, because any work sharing directive is across the entire team, which includes thread 0. So that's a slight. So I've seen people try and do this. It's really, I'll nominate a particular thread for doing the communication, and I'll use the other threads for calculation, and they can overlap. You have to be slightly careful. The way to do that within OpenMP is to use teams. Okay, well, is to have nested parallelism. Apologies. You explicitly only have an outer parallel region with 2 threads. One thread does this, the other thread goes here, and then within that you have OMP parallel over the remainder of the number of threads. Here you have to enable nested parallelism, because you have a parallel region within a parallel region. So this there may be lots of more overheads here. So serialized, it's easier for other threads to compute while one is in the MPI call. And you can also arrange, that's fun, sorry. So serialized, here in serialized, because each MPI, every thread can call the MPI library, although not at the same time, you can arrange for each thread to send and receive its own data. So you don't have this nastiness that all the data is at some point funneled through the parent process. Again, though, the disadvantages are it gets much harder to write and maintain. If each thread does communicate their own data, you're having a large number of small messages. And of course, if you have multiple threads calling the MPI library, because the MPI delivers messages between processes, it's up to you to manage the fact that you've got messages for different threads, and tagging is one way of doing that. So yeah, we've said that here. MPI receive will match. MPI receive specifies a source process, but not a source thread. You have to manage that either by lots of communicators, or probably most easily by using tags. Multiple is if you're a computer scientist, this seems the obvious thing to do, but the problem is in practice it's very hard to manage, and it's very hard for the MPI library to cope with this. Messages from different threads can in theory overlap, but actually, probably the MPI library is basically serializing. It's basically all its crucial operations where it actually does message passing are probably in critical regions. So it's easy for you. You don't have to worry about synchronizing the threads. You've offloaded that responsibility to the MPI library, but that may introduce lots of extra overheads. It's much harder to write and maintain. As we said, not all MPI implementations support this. A lot of them do now, but you could come across one which doesn't. And the main thing is most MPI implementations don't perform very well. Thread safety implemented could using global locks. So although multiple tends not to work very well. So there's a sort of summary here. MPI and OpenMP programs becoming standard practice. There says 30% of consumed CPU hours on ARCHER2. I think it's actually 30% consumed CPU hours were on the codes which had the ability to do MPI plus OpenMP. Whether people used it is a different question. People were, well, we are at the exascale now, but this was seen as the key to exascale. However, actually, this may have changed now that we have threading is the key to exascale, but it's threading on GPUs now, not on CPUs. So the logic of this may have changed. But correctness is hard, performance is hard, and as I said, even if you have a correct and performing code, you still have to basically worry about the choice of the number of processors and threads, and then the placement of them. So there's quite a lot of messing around to go on here. So you should think carefully about embarking on a mixed MPI and OpenMP solution. Remember Amdahl's law. the code design. So if you're designing a code from scratch to be hybrid MPI OpenMP, you can do that quite nicely. If your OpenMP is done at a loop-by-loop parallelization, this can be very challenging. And even with a good hybrid MPI OpenMP solution, as I said, you're using a package, quantum chemistry package or fluid dynamics package that supports it. You maybe need to do a lot of messy experimentation with flags and settings and such like. However, so I would say, think a lot about if you're going to go ahead with this. If you do, you need to use tools like XT-High and such like to check that at runtime you are putting your processes and threads in the right place. But people have seen benefits for this. So that's a bit of a whistle-stop tour. What I wanted to do was basically show you what the exercise is. The exercise is sorry. It's quite a simple one. I haven't given you a solution, I don't think. Let's think, have I? Sorry, I apologize, I should. Okay, so I haven't given you a hybrid MPI OpenMP code, but actually it's very, very simple. All you do, so if you look at the sheet, all you do is you basically take the MPI code and copy the small number of OpenMP directives into it. So basically, you add, all you have to parallelize two loops. There's the copy back loop in the main traffic.c, and there's the update loop in traffic.lib.c. And if you look in the pure OpenMP version, it's basically a cut and paste of those with maybe one change of variable names. So it really is 3 or 4 lines of OpenMP to hybridize in the master only model, in the very simple, in the simplest model. But then it's sort of interesting to see by playing around whether that actually helps with the performance. It probably won't with such a simple code, but it's interesting to see what the overheads are. So that is the exercise. As I said, I've given you a batch script in the C hybrid, which at least places the processes and threads in the correct location. Having done that, you should be able to quite simply hybridize the existing MPI program by copying the OpenMP directives from the OpenMP code, and then see if you get any performance improvements. Just one final thing before I just want to share what can easily go wrong. So I want to just share. Oh, I seem to have, apologies, mine. Okay, something straight. It doesn't want me to share the, it doesn't know. I'd lost my window. So hopefully you should see my window here eventually. Yeah, okay. So if I run XT-High. So now there's a nastiness. So I'm just trying to show you what can go wrong. So we saw that if we ran this correctly, we basically get, let's run it like this. Let's do that. So with the correct settings, oops, apologies, I always do this. I was messing around with the script, and so apologies for that. Okay. Right, so we can see that we're running 2 nodes. On each node, we've got 32 MPI processes, each with 4 threads. Are they in the correct place? Yes. Rank 0 thread 0 is on core 0. Rank 0 thread 1 is on core 1. Rank 0 thread 2 is on core 2. Rank 0 thread 3 is on core 3. And it goes up all the way up to 127. And then node 1 has the same thing. So that's exactly what we want. We have taken our MPI processes, we've placed them every 4th core, and the OpenMP threads are mapped to those reserved cores. So therefore, all the OpenMP threads are running in the same NUMA region as the MPI process, which is nice. There's a very nasty feature on ARCHER2 that this CPUs per task is not by default passed through to SRun. So you have to do this magic thing here. What happens if I don't do that? Okay. So that means that I've requested 4 CPUs for every MPI process, but I've not told SRun about it. What does it do? Well, let's run that. And this will show you what can go wrong. Now, actually, you get a lot of warning messages because ARCHER2 is a dedicated machine, and it says you've done something wrong. Okay. Now, but on your local system, it might not spot it. But so it's complaining. But why is it complaining? Well, you'll see what happens here. Sorry. So I have reserved. You can see here that all the rank 0 is on core 0. Rank 0 is on core 0. Rank 1 is on core 1, which is not what we wanted, and all the threads are bound to the same physical core. So this code will go a lot slower because basically it's all gone wrong here. I have bound the MPI processes toward 0, 1, 2, 3, 4 up to 31, and all the spawned threads from each process will be on the same core, which is exactly what I don't want. Now, ARCHER2 complains about that, but on your local system it might not, and all you would see is terrible performance. Okay, so I'm only using a quarter of the CPUs on each node, and worse than that, I'm oversubscribing them by a factor of 4 with each of the threads. So that shows you what you can go wrong. But I said the exercise is to do a very simple parallelization of the model and see if you get any performance. And I'll maybe talk about some results for that after the break. But the schedule now is that we'll have a lunch. Well, I'll be around. If you want to play around with the exercises, you can chat to me if you want. I'll be around till past, then a lunch break, and then we'll come back after the break. And I'm going to have to share